but I also need you guys to also memorize the larger ones too. So again, same typo that I've got here. This should be 10 to the 6, 10 to the 9, and 10 to the 12th. So after the kilo, I want you to think about mega, giga, and then tera. All right, let's keep going though. So dimensional analysis, when I bring that up, when I say those words, some of my chemistry students, they cringe and they're like, oh, I hate dimensional analysis. But it's all centered around these things called conversion factors. And conversion factors are not that hard. Most of you guys know them instinctively without me even teaching you. So like, for example, there's 24 hours in a day, there's 60 minutes in an hour. You know, time is something that you guys know really, really well. What you guys don't have very much experience in, or what you don't feel as comfortable with, is the metric system. So, for example, 1 kilometer is 1,000 meters, 100 centimeters is a meter. So we need to try to strengthen you a little bit in those metric conversions. Now, with conversion factors, the way that we use them in our math is we set up these conversion factors as a fraction. So down below, these are some examples of some conversion factors that are pretty common to you. So over on the left here, you guys are very familiar with the fact that 1 hour is equal to 60 minutes. They're equivalent. But what you need to remember is that when we use them in our math, we can use the reciprocal of the fraction. So if I put 1 hour over 60 minutes, that is exactly the same as if I said 60 minutes over 1 hour. It's the same fraction. Some people like to call conversion factors, when you set them up in the fraction form, magical ones, because they're equal to each other. So things that are equal to each other set on the top and on the bottom, if they're equal to each other, the value is 1, right? So for example, in this next one down here, 60 minutes is equal, or I'm sorry, 60 seconds is equal to 1 minute, but I easily could have said 1 minute on the top and 60 seconds on the bottom. The only reason why you are worried about conversion factors is because sometimes what we have to do is convert units. And when we convert units, we need to do one thing. We need to cross-cancel units. So let me show you some examples of conversion factors using dimensional analysis. Now, there are some rules that we need to obey when we are showing our work in my classroom. So you need to use dimensional analysis whenever we are trying to solve conversion problems. And when you do that, you need to make sure that you're showing all your work, that you are including your units, and make sure your units cancel out. And remember, everything on the top is multiplied and everything on the bottom is divided from the top. And please make sure that your final answer reflects the correct number of sig figs and includes units. Otherwise, you're going to be docked points, and nobody wants that. All right, so let's take a look at some real examples. Here's your first one. Let's convert 62.0 inches into centimeters. Now, the first thing that you probably want to do is map what you're doing. You're trying to go from inches to centimeters. The next step or thought process that you need to use is to figure out, do I know a conversion factor that can take me straight from inches to centimeters? Can it be done in one step? And when you look it up, sure enough, you see a beautiful conversion factor that will take you straight from centimeters to inches. There are 2.54 centimeters in an inch. So we can use that conversion factor in two different ways. Remember the fraction? So you can set it so that 1 inch is on the top and 2.54 centimeters is on the bottom, or you can do the reciprocal. You can flip that. Now, a note should be made here that we could have also said that 1 centimeter, the little guy, is equal to 0.394 inches. But as a general rule of thumb, most conversion factors, when we are in dimensional analysis, most conversion factors, the larger unit will get the value of 1. And that's just a typical rule of thumb. So either one is fine, just as long as your answer is correct and that you're thinking through the problem correctly. So the original problem started you with 62.0 inches. That is where we start our conversion factor. When you start your conversion factor, you always want to put what they gave you at the very top of the beginning of the problem. So this is how I would show my work using dimensional analysis. Start with what they gave me. I need to get rid of my inches, so I know that inches needs to be on the bottom so that it can be cross-canceled. So I'm going to make sure that when I use the conversion factor, inches is on the bottom to get rid of inches so that I have centimeters left on the top. Now, once you get your answer, there's only one final step. You need to make sure that you are reducing to the correct number of sig figs. So in the original problem, they gave you 62.0 inches. That's only 3 sig figs. So you need to round the final answer and make sure you show your units. All right, let's take a look at a real example next. Oh, sorry, I forgot. One more note. Notice that we did use a definition. We used the definition that 1 inch is equal to 2.34 centimeters. Now, I guarantee if you were to look this up in a scientific text, the conversion, you may find that there are, more sig figs than just 2.34 centimeters. But why did I only use 2.34 centimeters here? It's because the original problem gave me 3 sig figs. So I only needed to show 3 sig figs in my conversion with the inch. So here we have another great example, and I just wanted to show you an example where you're cross-canceling, not necessarily directly in order. You can cross-cancel in any order you want. So you'll notice that the original problem gave you miles and hours, and they're asking for feet and seconds. So I'm going to change the miles to feet, and I'm going to change the hours to seconds. So you'll notice that they're not directly next to each other. You see how I'm cross-canceling miles here, and then I'm cross-canceling hours here. So that's perfectly fine. And then you'll notice that you have 2 units left that are not cross-canceled. You got feet here and you got seconds here. And so look at your final answer. You see the units that are left? All right, this is perfectly fine, and you can do that anytime you want. All right. The next thing that we're going to talk about is how density is a conversion factor. So most students know that density is mass divided by volume, but did you know that you can use density as a conversion factor as well? Let's take a look at an example. So here is an example. We have density of gold, and the density of gold is 19.3 grams per centimeter cubed. So basically what this means is that if I were to have exactly 1 centimeter cubed, a little cube that's 1 centimeter, packed inside of here, there would be 19.3 grams of matter stuffed into that 1 centimeter cubed. So when you set this up, you need to realize that you can set it up as a conversion factor like this, or you can do the reciprocal like this. One thing that remains constant is that it's always 1 centimeter cubed. That's what density usually uses, is 1 centimeter cubed. That's kind of a universal thing. So here's a good example. It says, what is the mass of a chunk of gold that has a volume of 18.2 milliliters? And a lot of people forget this, or maybe you were never taught, but this is kind of one of those standard things that all chemistry students need to know. 1 centimeter cubed is equivalent to or equal to 1 milliliter. So you see how I have milliliters here? All right, so on these conversion factors, if you wanted to, you can actually say, instead of centimeters cubed, you could say milliliters, and it means the same exact thing. All right, a centimeter cubed is a milliliter. So you'll notice that in my conversion factor, I cross-canceled my milliliters and left grams on the top. Well, when you're doing this problem for real, you need to make sure that you also don't forget to reduce the final answer to the correct number of sig figs. And it looks like this particular problem has 3 sig figs. And now it's time to finally hit the last thing that we need to cover in this vodcast, the mole. All right, so hopefully this is a review. When we say the word mole, we're really talking about a really big number. And that big number is sometimes called Avogadro's number. It's 6.02 times 10 to the 23rd power. Sorry, that's a little typo there. And you can think of the mole as being like another word that you guys are familiar with. The word dozen means 12 things. Well, the word mole means 6.02 times 10 to the 23rd things. All right, when we use the mole, some other stuff that we typically encounter is something called molar mass. Molar mass is a mass of 6.02 times 10 to the 23rd things, and those things are usually really tiny, like atoms and molecules and compounds, and these masses have to be looked up on the periodic table. So in AP Chemistry, when we look up these masses, I have a little rule that we all need to obey. We need to make sure that we are using 2 decimal places in our molar masses when we look them up on the periodic table. So I'll give you an example of that in just a second. And then another factor or piece of the mole that you probably forgot is that the molar volume of a gas at STP, so 1 mole of gas at STP, will always occupy 22.4 liters. All right, it's been a while since you've probably reviewed some of these things, so let's take a minute to check this out. Does that look a little bit familiar? Okay, the mole! All right, so one of the things, I love this diagram, and one of the things you need to note about doing mole conversions is, for example, we can do straight conversions using Avogadro's number, so that's this part right here. We can do molar mass right here, and we can use what I like to call molar volume of a gas at STP, which is 22.4 liters here. But another thing that you need to make sure you realize is that sometimes we have to do more than one step. For example, what if I start on particles and I want to somehow get down to volume? The only way that I can go from particles to volume is first diving this way into the mole, and once I'm at moles, then I can go to volume. You see how there is not a direct connection between particles and volume. You have to use the mole in order to do that kind of movement. But for now, let's just keep it simple. I want you to know 3 conversion factors. You need to use Avogadro's number sometimes. You need to use molar mass, which you can find on the periodic table. And you need to use molar volume, which is 22.4 liters. All right, let's take a look at some examples here. So, if you forgot how to do molar mass, it's pretty simple. You need to use a periodic table, and you have to use the formula of the compound. So, for example, let's get the molar mass of water. Now, the formula of water is H2O. That means that you have 2 hydrogens and 1 oxygen. So you see over here how I looked up the molar mass on the periodic table of hydrogen, and remember we're using 2 decimal places now for our molar mass. And you see how I'm multiplying that value by 2 because there's 2 hydrogens in water. And you'll see here that I looked up the molar mass of oxygen. It's 16.00. And there's only 1 of them in the formula, so you see how I only multiplied it by 1. All right, so we have these 2 values, add them up, and you've got the molar mass of water. Voila. Now, on your guided notes, I'd like you guys to try one more formula on your own. Can you do this one by yourself, H2SO4? Please do that in your guided notes. Pause for a minute, look up a periodic table. You can find loads of them on the internet. I also keep a pretty good one for you guys on the first day of school. I'm going to give you guys a really nice periodic table. But until then, just look it up on the internet and pause the video here if you need to, and we'll continue in just a second. All right, so here you see 2 different examples. The one on the left, this is actually, as you can see, a 2-step problem. What I did is I gave you guys the mass of copper, and I wanted you to figure out how many atoms of copper were present. Now, in case you forgot how to do this, remember, come back up here. So I'm starting you on this problem with, I'm starting you with mass, and I'm asking you guys to get to the number of atoms. So here I am giving you mass, and I'm asking you guys to give me how many atoms there are. Well, remember how I told you sometimes we'll be using 2 steps? So in the first step, you're going to need to go from mass to moles using this guy right here. Once you get to moles, then you're going to need to go to atoms, right? So here you are at moles. You need to get your way to atoms, which is a particle. You need to use Avogadro's number. So you see how this is a 2-step problem? The only part that I don't like about the way that they showed their work, I pulled this example off the internet, is, I don't know if you saw this, but they only used 1 decimal in their molar mass. Just saying, in AP Chemistry, I want you guys to get into the practice of using 2. All right, so anyway, and you'll also notice a problem with their final answer, with the way that they reported their final answer. I would like you guys to try to do this problem correctly in your guided notes. I want you to use the correct molar mass for copper, and I want you to give me the correct number of sig figs in your final answer. So give that a shot. You got the basic idea here. Try it on your calculator and see what you get. All right, on the next problem over here, in this example, you are starting with volume in liters, and you are asked to give me how many moles. Now, if you think back to that diagram, this is a simple 1-step conversion. You just need to make sure that you start your problem with what they gave you and that you realize that you need to go from volume to moles. So you need to cross-cancel that volume, the liters. You see how they cross-canceled liters? And they put the 22.4 liters on the bottom. Now you need to do one final thing to this answer. You see this? Too many sig figs. So look at the original problem. This guy's got 3 sig figs, and then we use 22.4, which also has 3 sig figs. You need to reduce this to 3 sig figs. 1, 2, 3. Do you need around the 1? You sure do, because you've got that 8 right there. So the final answer should actually be reported as 2.22 moles. All right, everyone. I know that these problems can cause a little bit of stress, but I want to remind you that I'm here to help you. So if at any time you feel lost or if you need some additional assistance, make sure that you remember to talk to me first. You can email me. And also check the internet, check the website, our class website, because I'm going to be putting a ton of extra resources for anybody who doesn't understand any of this and needs maybe kind of a different approach. I have a lot of extra resources that I love to use. I've subscribed to many different channels on YouTube. I've got some of my favorites. So I'll be posting some additional resources for you, and make sure you check it out, okay? No stress, no worries. I want you guys to enjoy your summer, so I hope this video wasn't too long, and email me questions if you need to, okay? Talk to you guys later, and don't forget, you have another vodcast coming up. I'll talk to you guys later, though. Bye-bye.